Hello Chem 1A, this is Chapter 7, Lecture Video 3, and we're going to be discussing two more laws of gases, and that's Avogadro's law and the combined gas law. So Avogadro's law states that equal amounts of gas will occupy, at the same temperature and pressure, will occupy equal volumes. Now what this effectively means is when we're holding temperature and pressure constant, our moles and our volume are directly proportional, kind of like our volume and our absolute temperature are. In this case, we have an equation that kind of looks identical to the Charles law equation that we learned at the end of the last lecture video, and that is V1 over N1 is equal to V2 over N2. Now, this is our volume 1, this is our moles of gas initially, and our moles of gas final, right? Now, N has to be in moles. V can be in any unit you want, but N has to be in moles. So let's do an example problem. The volume of 4.56 moles of gas is 12.5 liters. Under the same conditions, what will be the volume of 2.87 moles of gas? So we have N1 is equal to 4.56, and we have V1 is equal to 12.5 liters. We want to know what V2 is if N2 is 2.87. We have our equation V1 over N1 is equal to V2 over N2, and we can just plug these numbers straight in, right? Because we have these guys in moles as given in the problem, right? So we have 12.5 liters over 4.56 moles is equal to V2 over 2.87 moles. And so if I rearrange this and solve for V2, I get V2 is equal to 12.5 liters times 2.87 moles divided by 4.56 moles. And solving for V2 gives me that the volume will be 7.87 liters of gas, right? As we look here, moles cancel, and we're left with liters as our answer. And so here we go. All right, so let's do the last law before in this video, which is the general gas law, otherwise known as the combined gas law. And this is where the only thing we keep constant is moles of gas. So pressure, temperature, and volume are all allowed to change in this equation, and we get an equation of P1 V1 over T1 is equal to P2 V2 over T2. Now, just like in the previous equations, pressure and volume can be in whatever units as long as they stay consistent across the equation, but temperature absolutely needs to be in Kelvin. So let's do a sample problem. We have an inflated balloon has a volume of 6 liters, so our V1 is 6.0 liters. At sea level, our pressure is 1 atm, so we know our pressure is 1.0 atms. And it's allowed to ascend in altitude until the pressure is 0.45, right? So now we have P2 is 0.45 atmospheres. During the ascent, the temperature of the gas falls from 22 degrees Celsius, so 22 degrees Celsius was our initial temperature, to negative 21 degrees Celsius. Calculate the final volume of the balloon, right? So we have V2 is what we're being asked to solve for. Now, before we do anything, we have to convert our temperatures to Kelvin, right? So I'm going to add my 273.15 here to get to units of Kelvin. And the same thing here, negative 21 degrees Celsius plus 273.15. This gives me 295.15 Kelvin for our T1, that was mislabeled. And for T2, we get 252.15. All right, so now we can plug this all into our equation, right? We have our P1, 1.0 atms, times our V1, 6.0 liters, divided by our temperature in Kelvin, 295.15 Kelvin, P1V1 over T1, that's the first side, is equal to P2 times V2, which is what we're solving for, over 252.15 Kelvin. And so we just need to isolate V2 here. So if we do that, we know V2 is equal to 1.0 ATMs times 6 liters times 252.15 Kelvin, all over 295.15 Kelvin times 0.45 atmospheres times, well, that's it actually. And so now we can solve this. If you look at the units here, the atmospheres are canceling there, the kelvins are canceling here, and our volume is going to be left in units of liters. And if we calculate this out to 2 sig figs, the volume rounds to 11 liters exactly. All right, if you have any questions, as always, please contact me and I'll be happy to help.